So our structures are like this. We have zinc oxide nanorods here, which are actually dressed with ZnFe2O4 nanoparticles. So the optical absorption is actually taking place in zinc ferrite here, ZnFe2O4. On the other hand, the electron is transferred to the electrode very rapidly by zinc oxide. So you use heterostructures where you try to use the positive properties of two materials and put them together into this particular device application. And what we have found here is that if you look at this particular thing, when you do a particular combination, you get, this is zinc oxide performance, this is zinc ZnFe2O4 performance, but when you make a heterostructure, the performance is dramatically high because of this charge separation and efficiency issues in terms of photoelectrochemical effectiveness. I will also give you another example. Once again, Fe2O3 and a much more accessible material. What we try to do is, you use N-type silicon nanowire array like this, and we try to deposit Fe2O3 nanoparticles on the top of that. So what we do is like this, that we actually spray coat Fe2O3 on the top of this silicon nanowire array. The reason for using silicon nanowire array is that it gives light harvesting property. So if you have a nanowire array like this, light comes inside, gets scattered and gets effectively trapped. So you get much higher, stronger light harvesting effect here, and you will see that it makes a huge difference. These are the kinds of wires on which spray coating is done, and this is just that. Let me point out here to your attention the following. Suppose I were to take Fe2O3, coat it on FTO, okay, I get this particular thing which corresponds to FTO band gap and everything. If I take Fe2O3 and put on silicon, which is like a single crystal flat silicon, I get this response here. This is actually a band gap of silicon. So it is a response over the whole visible range because silicon is absorbing it, okay. But if you look at the nanowire here, nanowire with Fe2O3, you look at the IPC here. I mean the internal photon to charge conversion, current conversion efficiency, it is dramatically high like this. So it is just putting things together in the right configuration makes a big difference. And you will see here that this is a photoelectrochemical response. When you consider the nanowire case, this is 1 sun intensity. This is 0.5 sun intensity. This is 0.1 sun intensity, which is very weak, like an evening sun. Okay, this is 0.1 sun. What you find here is that the response is not decreasing that much. But if you were to only use Fe2O3 or Fe2O3 on silicon, you look at the dramatic decrease here in this particular response. So we have here almost a low light category of trying to develop this particular application and so on. So a number of interesting things can be done in this situation. Let me now, in the last 5 to 7 minutes, what I will try to do is talk about another important, extremely important area, which is what is emerging now, and we have been working in this area, namely functional carbon and functional carbon-based nanocomposites. Many of us know all these fascinating forms which have come, but basically energy storage, namely battery and supercapacitor, as well as superabsorbents. These are the two areas where carbon is making very, very interesting contributions now. Now, let me show you one example of our recent work. One of my students, what he tried to do was, he used a Fe containing metal organic framework, a MOF system, MOF, metal organic framework, an iron containing MOF, and of course, he used the MOS spectroscopy to see that it is in Fe3+ state, which is what is expected for this particular MOF. Then he tried to develop carbon materials starting with this MOF. These MOFs are, as many of you would know, these are very open structures, and when they crumble under pyrolysis or under radiation treatments or something, they form highly porous structures in this way. So what he tried to do was that in one case, this is, by the way, this is the way the MOF look like, and these are the kinds of crystals which are micron size that we generate. He used this, and in one case, he annealed it in argon atmosphere, reducing atmosphere, and produced Fe3O4 carbon nanocomposite. What he got was the Fe3O4 carbon nanocomposite. On the other hand, in another case, when you heat it in air, you get highly porous Fe2O3, alpha Fe2O3. The phases have been confirmed, of course, by Morse spectroscopy. Now, this is again the same types of MOF structure that we are showing. Let me just skip this. This is how the composite looks like that we get, and it is mainly Fe3O4 with some component which is which is at the center, and this is you get a structure which is carbon loaded with Fe3O4 nanoparticles in this way. Now these kinds of things can be used in interesting ways for applications in the following way. For example, if you take this material and if you disperse it into water, these are the kinds of dyes. Okay, this is Congo red and this methylene blue and so on and so forth. We place this particular material, stir it with it, and then you put a magnet, the whole dye is gone. So you are trying to use the magnetic Fe3O4, okay, to pull the material, clean the dye. Because there is a lot of industrial waste in terms of dyes and everything which people throw out, and it goes into the water system. And you need things to sweep and clean them in one way or the other. So this is the way it can pull this. You just disperse like this and pull it. Okay. And of course, what we can do is we not only pull it, but we go through the cycle like this to get the dye separated out. So it is like this. This is the dye in water. You put here, you recover the dye, put with a magnet. Again, you recover the composite. You get here, again dispersing ethanol, then clean again with a magnet and get the dye. So we not only, if there is a debris, we not only take out the dye from there, but we recover it again for possible reuse through ethanol water multiple cycle processing, and it is possible to get it a clean dye in this particular way. There is another thing that one can do is oil cleaning. For example, if you look at this application, this is a petri dish on which we have oil spread here, and we spray here the so-called magnetic carbon, meaning magnetic carbon composite, not magnetic carbon per se, but Fe3O4 carbon nanocomposite. This particular composite is processed slightly differently than the one which I showed you in the previous example of a dye, because this one is hydrophobic, so it floats on the water, the carbon. The previous one was partially hydrophilic, so that it goes inside the water and tries to get the dye from the water. In this case, the carbon itself floats on the surface of water here, and then if you mix it, just stir it, and with a magnet you clean the whole water like this. And you can see that this is absorption capacity. What it is showing is in the first cycle, this particular carbon is absorbing 40 times its weight. 40 times its weight of oil it is absorbing in this particular way. Okay, and you recycle the oil, clean it back, clean it and reuse. Finally, over time, in equilibrium, you almost settle like 28 times of its weight it is absorbing. So this is a problem where many of you may know, of course, everybody knows about this oil spill near the beaches and so on. There is a lot of interest in collecting the oil, and we are just trying to envision that if there is a large area, you can have this kind of functional carbon thrown on the waterway, and then it automatically stirs, and then there is a motorboat with magnet passing, collecting the oil and so on. There is no harm in cleaning in this particular way, and this is the oil spill that one tries to generate. We have also done other things that I said, if you look at the same particular material by using MOF but oxidizing atmosphere, heating it in oxidizing atmosphere, we are generating Fe2O3, but this is highly porous. And you can see also that we are using very high battery characteristics in this particular way. So the same material, you start with MOF, metal organic framework, crack it in one case with argon, a reducing atmosphere, you generate a magnetic Fe3O4 carbon composite. Another, you do it in the oxidizing atmosphere, you generate a highly porous Fe2O3, using that for the battery purpose or storage applications and so on. Very interesting things can be done in this way. Again, this is the same result. I will show you another thing, that one interesting thing that we are trying to do is this category, waste to wealth. This is from the standpoint of environmental applications. What we see is, especially in India, what we see is many times, these are the leaves which fall on the road somewhere. People just sweep them, collect them and burn them. Okay, and when they burn them, there is a lot of CO2 and everything and soot and everything coming out, and it is going. And these leaves were falling just outside my office, so I was all the time seeing that somebody is collecting and so on. So we said, let's try to see if we can make some better use of these leaves and so on. So we just brought them and we crushed them, produced them in a mixer pellet, and then in a reducing atmosphere in a controlled condition, we got it, and we got a very highly conducting carbon. And the carbon was very highly porous like this. An interesting aspect about this is, when we did this, these leaves, in addition to the organic matter which contains carbon, they also have certain oxides, certain small almost nanoparticulates of MgO, some other kinds of calcium and so on and so forth. And when we do acid treatment of this particular product, we get extremely high capacitance values, almost like, you know, a few hundred farads per gram and so on. You know, so these are very interesting applications that we see. I'm done in 2 minutes. Yeah, okay. So there are other things that can be done also with a carbon, meaning we are using laser beams actually to produce very interesting morphologies of carbon system, as I have shown here. You can use, and also what we are trying to do is we are producing these morphologies using pulsed laser treatment of liquid systems to generate carbon. We are also dressing them in interesting ways with various types of metal oxides for energy applications. Let me show you another case of interest where we are trying to do large-scale laser synthesis of Fe3O4. For example, what we did was we took excimer laser pulses. We simply take bulk Fe2O3 in ammonia solution. We put like that, blast it with certain laser pulses, and we get completely black color powder, which is magnetic. So we generate Fe3O4. We want porous iron oxide for certain energy storage applications. And you will see what is happening. This was the original alpha Fe2O3. Now after laser blasting it becomes black, and if you put a magnet, the whole thing goes there. So it is completely like a mixture of Fe3O4 almost forming here. And you form here that the morphology originally is like this, and later on after laser hitting you generate mesoscopic particles like this, which are quite porous, and we are trying to use them for different applications. Interestingly, if you look at various properties there, the magnetism and so on, we see that the Mossbauer spectra evolve in this particular way, and what we find from relative contributions is that we are actually getting a mixed configuration between Fe2O3 and Fe3O4, and the relative contribution, initially we start with Fe2O3, no Fe3O4, but as you keep on blasting laser, we get a mixture of both. But remember, this is a composite. These are not two separate powders, because when we pull with a magnet, the whole powder comes together. It is not that some powder is remaining, which is alpha Fe2O3. So this is a composite mesostructure which is porous that we are creating, where you have a mixture of Fe2O3 and Fe3O4, probably in the coaxial configuration, which we are trying to use for certain energy applications. Let me just show you. This is my research group. I have about 25 to 30 research students in my group. All are extremely bright. They come from various parts of India, and you know, because of them we are having a kind of a diverse program in different activities. This is me, and there are certain programs, there are certain interns and so on. So very active group that we have. We have an activity in various areas. We have a kind of infrastructure which you can see here, and it is growing sort of. Our main main work is now on graphene CNT and dye-sensitized solar cell, optoelectronics and things of that nature. So there are lots of things which can be done, and I would be very happy if there are some interesting suggestions for collaborative research. We will welcome that. Finally, I will just say that in the environment and energy context, it is very important that, as it is said, it is all in our hands, whether we want to burn it or whether we want to protect it. This is very important to think about it and contemplate. And this conference is the right forum to do this. Thank you very much.